So on Friday, we were looking at maximums and minimums. And we added the idea of looking for an absolute max or an absolute min in some particular region of the plane. We gave an XY range, an X range and a Y range. We have this little rectangle or a circle or something. But I want to add a different idea. Something we did back in Calc 1. So my function that I'm going to maximize will be this function f. So I want to find the biggest and smallest value of f of xy or f of xyz. And then I throw this extra equation at you and say we are restricted by this. This g of x, y, g of x, y, z function, this g function could have nothing to do with f. It could be completely and totally independent. But it's our restriction. We've done this before. I asked you to find the largest box that we can make by cutting the corners off and folding up the sides, right? The box had an open top. But I said the base had to be square. That restriction meant that all the corners that we cut out had to be square. So that's this sort of restriction here. But in this case, they could be any two equations. Let me try and visualize this in a function of two variables. If I have a function of two variables, then that's a surface, right? So I have some 3D surface here. And then I have this other equation that is fixed, g of xy equals k. That's a particular level surface, level curve of the surface G. Let's overlay those together. I could have something that looks like this, where in red we see the level curves for f of xy. But then G is one particular curve, and I want to find the spot on this curve that has the largest value of f, which means I need to go as far as I can in G to get f to be as big as possible. Wait a minute. We talked about the direction in which f has its biggest change. What was that symbol that we came up with last week? F changes the fastest in the direction of the gradient. Exactly. So f is changing fastest in the direction of the gradient of f. G's change, without the k on it, G's change as a surface is in the direction of gradient of G, right? And if I want to know where on G is f changing fastest, I need to match up those rates of change. So it turns out that the best way to find this spot is to find out where my gradients line up with one another. That means the gradients are parallel vectors, because the gradient's a vector. I want gradient of f parallel to gradient of G. And I still want G to be equal to K. So I still need this equation. To make sure I'm on the right level curve of G. How do I know if two vectors are parallel? The exact same equation? It's a multiple. So that means I need a name for this number. I've already used X and Y and G and K and F. I know, I'll use lambda. So I end up with a bunch of different equations. I end up with this. I end up with this. Now, if f is a function of x and y, that means I end up with two derivatives, partial with respect to x and partial with respect to y. And I have two derivatives for g. So I'll set the x parts equal, I'll set the y parts equal with that lambda in there. And then I'll have a third equation. That means I have three variables, x and y and lambda, and I have three equations I can solve. If I'm in 3D, then g and f are both x and y and z. So I'll have three equations, the x part being equal to the x part, the y part to the y part, the z part to the z part, and I'll have the equation g, and there's my fourth equation for the lambda floating around. I can do this no matter how many variables I've got. That's a great abstract idea. Let's not do it in abstract. Let's actually do an example so it doesn't look like I'm just talking out my ass. So here is such a problem. I want to find the points on a particular hyperbola, xy equals 1, that are closest to 0, 0. Measuring the distance requires me to use the distance formula, right? So I want the points that are closest to the origin What's the formula for the distance from a point xy to the origin 0, 0? Chapter 12, section 1. It was a long time ago.
That's square root of 0 minus x squared minus plus 0 minus y.
Yes. And because I'm subtracting with 0, I just get x squared plus y squared under there. My first unhappiness about this is that there's a square root. I get to cheat. I am measuring distance. Distance is always bigger than or equal to 0, yes? Which means this graph is a strictly increasing function. Because that's the distance from 0 radially, right? Square root of x squared plus, that's r, polar coordinates. So that means I can actually make my life easier and square this function. And if I find the minimum of f squared, that's the same as the minimum of f, because the square root is strictly increasing. So instead of using the square root, I'll just use x squared plus y squared as the thing I am trying to find the minimum of. And notice we have our restriction given to us in the problem. The g of xy part, g of xy equals a number. That's our hyperbola, xy equals 1. That's our constraint. Well, now I can set up my parallel gradients. What is gradient of f? What is gradient of g? Gradient vector is the vector formed by the partial derivatives. So gradient of f is partial with respect to x, partial with respect to y. Partial with respect to x and with respect to y. Same questions in g. Partial with respect to x and partial with respect to g. With respect to y. Now I want these to be parallel, so I need lambdas in here. But in order for two vectors to be equal, their parts have to be equal. So this gives me two equations. And I also have the equation g of xy equals 1, or whatever the constant happens to be. So here are my three equations in three variables. How convenient. The biggest problem involved here is solving those three equations simultaneously. They're not linear equations. I can't use a matrix. There is not an easy and obvious necessary way of solving these. But I could go back and use all the tricks we used for nonlinear equations way back in algebra class. How many years ago was that already? Oh boy. All right. How do I solve these together? I'm going to number the equations just to keep my crap straight. Take the first equation, equation 1, and multiply it by y. Hey, wait a minute. What does equation 3 tell me? xy is equal to 1. Notice I can do the same thing with equation 2, only instead of multiplying by y, I'll multiply by x. But again, I see an xy on this side, and I know that's equal to 1. Well, that actually helps me. You see the looks on your face. That helps. Well, if lambda x squared equals lambda y squared, because they're both equal to 2, then I can divide by lambda. Because lambda is a number. And it's got to be a non-zero number, because otherwise I would just be saying that the gradient is 0. And that's not what I'm after. I'm after these two vectors to be parallel. 0 has no direction. It's not parallel to anything. Take the square root, so I get that x is plus or minus y. And again, why does that help me? Go back to equation 3. X times y equals 1. It means either both these numbers are positive or both these numbers are negative. If they had different signs, then when I multiply them together, I get negative 1, right? That means that x is actually equal to y. Which means you can solve for x and y now. With equation 3, because equation 3 says x times y equals 1. And x and y are equal. I claim those two are the points on this curve that are closest to the origin. Wait a minute. xy equals 1. That's the graph. Y equals 1 over x, right? That's our hyperbola. Let me square that picture up so it looks a little better. Zoom option 5. And if we draw the closest spot to the origin, wouldn't that be at a 45-degree angle? The distance from 0, 0 to 1, 1 is the square root of 2. That's the closest I can get. Any further along that curve, I'm farther away. Because the gradient of f is going towards the origin or away from the origin as fast as possible along that line. Gradient of g is also pointed perpendicular to my level curve. Isn't that what we came up with in 15.7? Sorry, 14.7? That's how we could use it for level surfaces. And it would get us a tangent plane. All of that information came from what we know before. Perfect, wonderful. The restriction is the reason I can't use the second derivative test. Because if you were to ask me, what's the point with the smallest distance to the origin? Well, that would be the origin itself, right? So it's taking that extra restriction that equation 3 gives me into account by doing this process. Questions? Nearest and furthest distances come up a lot. There are applications in higher dimensions. Here's a variation of this problem. Find the points on the sphere x squared plus y squared plus z squared equals 4. Wait a minute. That's a ball of radius 2 centered at the origin. So all of the points on that are equally distant from the origin. That doesn't help me. But let's pick another point. 3, 1, negative 1. 3, 1, negative 1. What's the point on the sphere closest to that? What's the point on the sphere furthest away from that? Why do I care? Well, let's make this the Earth, and that point the location of a GPS satellite. If I know what point is closest, that'll be the point with the shortest time to communicate to. The point furthest away should be on the opposite side of the globe from that, yes? I find antipodal points on the globe. I know where those two are. I can draw the circle that cracks the globe in half right there, yes? The satellite can reach every point on one side. Can't reach any points on the other side. I found the dark side of the moon. Pink Floyd was right. How do I find this? I'm using distance. My function f is going to be the distance from any point to this. But I'll get rid of the square root. The square will help me get rid of the square root. And again, I'm doing that because distance is always positive. So that gives me, well, let's just ignore the square root. X minus 3 squared plus y minus 1 squared plus z plus 1 squared. Set up the gradient equations. And remember that the G is the equation involved in our restriction. The numerical value only comes in when we do the solving. So to do the gradients, I need the derivative with respect to x. What do I get? Both.
And after you get 2 times,
And then in G,
you get 2.
but I'm going to need the lambda over there, right?
Yeah.
Because it's gradient of f equals lambda gradient of G. What about the y part?
Same thing with 2 times y minus 1 equals lambda 2y.
And then 2z plus 1 equals lambda times 2z. And then there's my fourth equation. 4 variables, 4 equations I can solve. Now again, I will say part of the problem is that this is not particularly obvious about a method for solving, right? This is kind of ugly looking. I got a whole bunch of extra 2's up here though. That bothers me. So let's get rid of those 2's. Let's just work with the first one. That becomes x minus 3 equals lambda x, right? Ooh. If I could write this as x equals, then it would be in terms of lambda, right? Notice that the second equation only involves y and lambda. I could do the same thing there and write y in terms of lambda, couldn't I? And then in the third equation, I only have z and lambda. So I could write z in terms of lambda. Do that. Get me y equals and z equals in lambdas. What do you get?
Y equals 1 over 1 minus lambda. 1 over lambda 1.
That's the only one that's backwards, right?
Yeah.
So let me switch that. I'll put 1 minus lambda on the bottom. I'll put a minus 1 on top. Then they're all kind of the same, right? Okay. I've only used equations 1, 2, and 3. Equation 4 has x squared, y squared, z squared. I can turn that into an equation in just lambda, can't I? And now, Noah, look at what happens in the bottom. They're all 1 minus lambda quantity squared, aren't they? So this is 9 over 1 minus lambda squared plus 1 over 1 minus lambda squared. And when I square a negative, it becomes positive. But that means on the left, I just have one fraction in lambda because they all have the same denominator. I can solve for lambda. Cross multiply. 11, well, let's just swap them. 11 over 4 equals 1 minus lambda squared. So 1 minus lambda is the square root of 11 over the square root of 4. I took a square root, plus or minus. Again, I'm going to switch sides. 1 plus or minus root 11 over 2 equals lambda. One of those should give me the closest point. One of those should give me the furthest away point. Plug in to x and y and z. So, if lambda is 1 plus root 11 over 2, then x is 3 over 1 minus lambda. That's 3 over negative root 11 over 2, because the 1's will cancel. That's negative 6 over root 11. Which I'm going to leave just like that. I'm not going to bother to simplify it at all. I don't care what the decimal is. That really doesn't matter to me all that much. Y is 1 over 1 minus lambda. And z is negative 1 over 1 minus lambda. What happens if I use 1 minus root 11 over 2? All the signs just flip, because instead of having 1 minus lambda be negative, 1 minus lambda will be positive. One of those is the closest point. One of those is the furthest point. Furthest or closest to what? 3, 1, negative 1. X is positive, Y is positive, Z is negative. This one's close. This one's far away. Notice it's exactly on the other side from the same sphere. I've got a heat source. The closest spot will be hottest. The furthest spot will be coldest. Questions? Please notice that 90% of our time in this problem was spent on algebra, not calculus. So if I'm doing this in real life, what am I going to do with this set of equations? Just shove it in the wolf's mouth and say, go. Absolutely. And if that's the case, then it is probably to my benefit to even more so think about what happens when I get more restrictions. This example asked me to find the maximum value of a function of three variables on the curve that is the intersection of this plane and that cylinder. Two different restrictions and a function. That means my gradient needs to be parallel to the first restriction, and it needs to be parallel to the second restriction, which means instead of having one equation with one gradient, I have the sum of two gradients. Multiply the first one by lambda, and the second one by something else, mu, L and M, right? We'll use sequential letters. And that's going to give me a fifth equation because now I have five variables. There is no way on God's green earth I'm going to do this by hand. I'm going to take my five equations in five variables, and I'm going to shove them into a computer. And I'm going to get an answer. Now, the textbook actually does do this by hand, which I think is psychotic. Because they say, hey, wait a minute. I know lambda equals 3. Let's just plug that in up here. And then I can solve for mu, and then I can use those down here. Blech. I'm not doing that by hand. If I can set these up, that's enough. And I find that to be true even in problems like this one. If I can set up the system of equations that I want to solve, the algebra is easy. Leave that to the computer. But if I tell the computer to find a maximum, even a large language model is not going to know what trick I need to do. I'm going to have to say, I want to use Lagrange multipliers to do this. And then things like Wolfram alpha will say, oh, well, what are your two functions? Then I can go do that. But it's doing the symbolic same we were doing. So if I can set up the equations, that's easier on my end. Questions? I remember very distinctly optimization problems from Calc 1. Find the biggest box, the largest volume we can make. Find the biggest trapezoid that fits inside a circle. Remember that one? That was a homework problem I assigned. Where is optimization in here? Chapter 4, section 6, 7. Here we are. Optimization problems. Find the area of the largest trapezoid that can be inscribed in a circle of radius 1, whose base is the diameter of the circle. There we go. But now, I don't have to restrict myself to using the base being the largest chord in the circle. I could say find the largest square that fits inside a circle, largest rectangle. I could even change the restriction. Make it not a circle. Find the rectangle with the largest area that can be inscribed in the ellipse x squared plus 4y squared equals 4. Oh, that's disgusting. But I think it's more disgusting because I don't know what it looks like. But I know what that ellipse looks like. If I set y equal to 0, I get x squared equals 4. If I set x equal to 0, I get y squared equals 1. I want you to put a rectangle inside here. I have no idea where I should put that rectangle. But I know the corners have to touch this shape, right? And if it's a rectangle, the sides have to be parallel. I think if I put it in an angle, I'm going to have a lot of trouble. So let's put it squared, parallel to the axes. If this is squared up, then I know that I can get the coordinates of these 2 points based off of this one. If that top right corner is xy, what is the bottom right corner? Top right is xy. And what's the top left corner? And that means this bottom left corner is negative x, negative y, right? What is the area for this ellipse? For the rectangle, not the ellipse. It's the area for the rectangle. Length times width. The length is x minus minus x. Difference between those two. And the height, which means the area of this ellipse is given just from knowing those two numbers. The area of the rectangle. I have not said that twice. I apologize. It's 2x times 2y, which is just 4xy. That's the thing I want to find the maximum of. And you have the restriction that is the ellipse itself. Set up the equations for me. By the way, since I've called this function a, I won't call it f. That'll be my f of x function. So it's the gradient of a is equal to lambda times the gradient of my restriction and my restriction itself. I need 2 other equations inside that brace. What are those 2 equations? And
4x equals 8.
ta-da. Now again, I'm not thrilled looking at this. But I could take each of these equations and solve for lambda. Because I know neither x nor y can be 0. Why do I know neither x nor y can be 0? An area of 0 is definitely not the biggest area I can make. So from equations 1 and 2, I get these. Wait, this is reducible. This says that 2y over x, and this says x over 2y, and those need to be equal to each other because they're both equal to lambda. Well, the only way that's going to work is if x squared is equal to 4y squared. Take this and put it right here, and you can solve for one of those two numbers, either x or y, using the ellipse itself. If I set the 4y squared equal to the x squared, I get x squared plus x squared equals 4. So x squared is 2, and that makes x plus or minus root 2, except I really only get one value. Why? Why do I only keep the positive one? But that area function has x and y in it, so if x was negative, maybe y would be negative also. But I know x has to be positive because when we drew the picture, we put x in the first quadrant. X has to be positive right there. And since up here I have x squared equals 4y squared, I have y squared is 1/2, which gives me y equals 1 over root 2. And there's the point xy that will give me the largest area. And the area is 4 times x times y, but x times y equals 1 here. So my biggest area is 4. I have absolutely no idea when you're going to have to try and put a rectangular window in a round hole, or an elliptical hole, or some unusually shaped object inside another, but I've been in construction sites that do this weird all the time. So I think it's useful for us to be able to solve these problems. I would recommend that you read through the rest of the examples in this section rather thoroughly. This is the end of chapter 14. Next Wednesday, question and answer. Thursday, this homework is due. Friday's our exam. I will see you all on Wednesday. Have a wonderful rest of your day.